probably should have put those announcements on Screencast-O-Matic too. I just forgot to. Let's see what this slide says. Yeah, this is that next problem, I think. Okay. Any questions on anything we've done so far then? All right. I believe this is example 6. Okay? Now that's not a form. Let me blow it up some so you can see it a little bit better. And they've done something there, but haven't shown me how they did it. So I got to fill in the gap. This is the problem here. Don't forget about this here. That's the problem. Well, that doesn't look like any of our forms, does it? Okay. So I bet if I were to quiz you, one of the favorite things you had to do in algebra was completing the square. You just enjoyed that so much, didn't you? Yeah, I thought so. Okay. We're going to complete the square. So there's the problem. X squared minus 6x plus 11. Yeah, that's it. So in order to write on that, I've got to shrink it back down again. So what we're going to do is get my pen activated and get the colors I want. Okay. So let's take the x squared minus 6x plus 11. Whoa! What's that big gap there for? Completing the square. It's the same problem, it's just got a little space in it, right? So I haven't changed that denominator. I haven't put the squares on it. Just this part here, that's the same as that, just with a blank there. Now, why did I put a blank there? You remember how to complete a square. Silence means no, okay? Let's go back. Give me a number and or a variable. I don't care. Just a variable, just a no. Either a variable or a number with a variable. 12 with a variable.
4x.
Or 4x. Okay. 4x. Want it plus or minus? Plus. Okay. And then give me either a variable or a number with a variable or just a number. I don't care. Huh? 20? Okay, he's a glutton for punishment, isn't he? Okay. You're going to have to do it. Okay. Now what I want to do is square that thing. You remember how to square it. You chose these numbers, so don't write. Say again?
X squared. So it would be 16x squared.
16x squared. Okay. Plus. Say again?
Would it be 400?
Oh, okay. That part would be 400. You're right. But you left out a part, didn't you?
Plus 8x.
Try. You remember? Okay. If you don't remember how to square a binomial, you do remember how, because squaring is 4x plus 20 times, you chose the numbers now, times 4x plus 20, right? That's squaring it, right? So let's multiply. 4x times 4x, 16x squared, outer, $80x plus 80x is 160x. You double the middle. And then plus 400. See, he's smiling too. Okay, never mind. Okay. All right. You like my happy face? Okay. So, that's how you square a binomial. So how you come up with a perfect square trinomial, the first thing you do is, okay, it's a lot easier when you don't have a coefficient here, okay? So if you had a coefficient here, factor it out and just deal with the 1, coefficient of 1, okay? So if you don't have to worry about that, then the first thing you did is here, if you didn't have to, let's go back and do that then. It'll be a little easier and it'll be a good review too, okay? Let's just do this one now. Well, that could have stayed the same thing. I'm going to lose my happy face. Okay. Now, square that one. X squared, got it. 40x 400. Okay. So it's a lot easier if that first coefficient is 1. Okay. So how did you do this? You just squared that. You squared that. But this was twice the product here. We already have the x squared by itself here. That part's done. Okay? And whereas here, you twice the product here, to get from here to there, you would take half of this, wouldn't you? So that would be minus 3x. Right? Okay? Now, as soon as you determine that that's a minus 3, on down on this line, we're going to x minus 3 squared. But what you do up there is minus 3 square it. What's the square of minus 3? Square minus 3. Plus 9. Okay, I've just changed the problem. It was the same problem, but I just changed it, didn't I? Can't do that. Okay? Unless I subtract 9. And now it's the same problem again, isn't it? Yeah. Okay? But this part right here is the perfect square of x minus 3. Right? X minus 3 squared. If you don't believe it, follow it. You see? That is the same. And then what you have here is a plus 11 minus 9 is plus 2. Okay? You see that? All right. Now, so let's go down to our thing down here. What we had here is this. Okay? This thing is the same as that, right? Now what we have in your denominator here, though, it was squared, right? This thing here that we just filled with, squared. Okay? Now, if you think that's a little messy, we can do a substitution there. And let u equal x minus 3. Let u equal x minus 3. Then what's always our next step in substitution? Du is equal to 1. 1 what? Okay, dx. Okay, good. It's equal to dx. Okay. All right. So, what our integral was here, the integral of dx over this thing squared, we said let u, that is the same as that thing. u equal x minus 3 squared. No, u equal x minus 3. So now we have, the first half of this is u squared plus 2 squared. du dx. You see that's equivalent, right? So this becomes our new problem. So if you have any old trinomial down here, you can always complete the square and then do a substitution and get it into this one. Is that form any better than anything else? How could we solve that problem? Yeah, one of the things. That's it. Okay. We'll do one of the things. Okay. And which thing will we do? We'll do a tangent. So we'll let what? Say again? Let. You said tangent. What's going to be tangent? Not yet. U. We'll use this, the revised form. Let u equal, is it just tangent? Okay. Say again? You may have said it right, I just don't hear well. If that were 2 squared, it would be 2 tangent. It's not 2 squared, it's just 2. So that would then be the square root of 2 tangent. What do you want to use? Theta, I thought so. One of my favorites. Okay. That's going to be our substitution. Then, we got a few thens to do. To the right, to the left, so sit down. Okay, whatever. What you want to do next? du, okay, then du is equal to square root of 2 is just square root of 2. Secant squared theta d theta. All right. You're my d theta person today. Okay, good. All right. Now, that takes care of the du. We've still got to do a u squared. So what's u squared? 2 tangent squared theta, right? And then a u squared plus 2 would be 2 tangent squared theta plus 2, right? And then if you, what is that? That is 2 times tangent squared theta plus 1, right? What's tangent squared theta plus 1? What is it? Secant squared theta, okay? So this is now running out of room. Secant 2 secant squared theta. Okay? But we've got that thing squared. So this thing squared, it's u squared plus 2 squared. Okay? So that's going to be, so let's see if we can write it all down. This will be 4 secant squared theta, no, secant fourth theta, right? When you square 2 secant squared theta, you get 4 secant fourth theta. So let's go back to our integral. The du is the square root of 2 secant squared theta d theta, right? Agreed? Right? Okay. That whole denominator there, the u plus 2 squared, is this thing. 4 secant fourth theta. Right? Right? All right. What I'm going to do is take out the square root of 2 over 4. Okay? And then the integral is going to be, and the secant squared thetas cancels out 2 of those, leaving you, this goes on the outside. Okay? That leaves you 1 over secant squared. What's 1 over secant squared? Cosine squared. So we got a cosine squared theta d theta. All right. Rapidly running out of room. Can we integrate cosine squared? The answer is sure we can. Okay, how? One of the things. Why didn't I think of that? Okay. What thing would that be? Go in the handy dandy table. It's number 4, right? Okay. You want to call it out to me? I'm going to put the square root of 2 over 4 because that's there. And you tell me what number 4 tells you to do. Okay, now which one are you going to do? The second one. So it's not an x now, it's a theta over 2 plus 1/2 sine theta cosine theta. Okay, now we can put the plus c now if we want to. I'm kind of all in favor of waiting a little while on it. Is that okay? Okay. Now, let's go back to where we first made the substitution. It was right here. That let u equal square root of 2 times the tangent of theta, right? Right there. See it? Got it. Okay. Now, let's divide by square root of 2. Okay? So divide both sides by square root of 2. So these go out. And that yields us tangent theta is equal to u over root 2. Right? All right. Now, don't have a lot of room. Let's draw us a little triangle down here. Okay? It's supposed to be 90 degrees there. Just pretend it is. If this is theta, what are your 2 dimensions you can tell me from that expression there? Opposite is u, adjacent square root of 2. Okay? So opposite is u, and this is the square root of 2. Okay? Now, here was our answer, right? Now, here's one thing I'm going to do, if it's okay with you. Okay? I'll make a rhyme every time. Okay? I'm going to factor out the 1/2. So I'm going to make this square root of 2 over 8. Is that all right? That way I don't have to worry about this fraction. Get all the numbers on the outside. So let's make this the square root of 2 over 8. Okay. Now, from this expression here, that tangent theta is equal to u over 2, we can get what theta is. What will theta be? This expression here, can we get theta by itself? How? Arc tangent or inverse tangent of u over 2. So this theta becomes, I pulled out these and made it 8. So this will be the inverse tangent or arc tangent of u over root 2. Right? That's what you told me, wasn't it? Okay. Plus, now, I need sine of this angle theta. What is the sine of that angle theta? What? What's the sine of this angle? That's what we do in the exercise. So we got this theta to be inverse tangent. Okay? Inverse tangent of u over 2. Okay? Pull out this theta. Okay, the next thing we run into here is the sine theta. What's the sine of that angle theta? Oh, we don't know the hypotenuse, do we? Or do we? What is it? Second. That thing again, okay? It's going to be the square root of u squared 2. That's it. Okay? So sine theta is going to be u over the square root of u squared plus 2. Right? And what's cosine theta going to be? Say that again. Okay, square root of 2 over. Say again. Square root of u squared over plus 2, right? Do I have it right? All right. Now, I've used every little bit of space I can. So, I need to erase some stuff here. Sorry about this. This is one place working on the board was nicer because I could get everything up there at one time. I can't on this little bitty screen here. Okay, so what I'm going to do is erase this because this was your scratch work that I had to convince you could complete a square. Remember? I should have erased this as soon as we finished it. This sure has slowed down. Okay. And I think I can probably get rid of this too, can I? Pretty sure I can. We've already used it. I sure hope I don't need it again. Oh, I bet we will, but too late now. Sure is slow. Okay. I think I'll go and get rid of this one too, because I can reproduce that if I want. Okay. Okay. So this is what we have so far, right? Let's clean that up a little bit. That integral is equal to pen's not writing very well. Okay. root 2 over 8, okay, times inverse tangent. Arctangent is fine, it just takes more room to write, and I don't have much room, so I write inverse tangent of u over root 2 plus, now, this is multiplied, so I can simplify that a little bit. I'm going to put u root 2, and when you multiply the denominators, that just gives you u squared plus 2, right? All right, so that's simplified a little bit. We still need a plus c out there, let's not forget that, okay? But now, all we have to do is go up and plug in what u is, or u are. What is it? X minus 3. So, our answer now appears to be the square root of 2 over 8 times the inverse tangent of x minus 3 over root 2 plus x minus 3 times root 2 over, and guess what? This u squared plus 2, oh, I knew I would need it. The u squared plus 2 is that thing right there, right? Right? Because u's x minus 3, so this is u squared plus 2. Forget about this. So that u squared plus 2 is this thing right here. That's what we started with. So our denominator now is, in terms of x, exactly what we started with. X squared minus 6x plus 9. Okay? Second? Oh, you're right. It's plus 11. That's what we started with. I forgot that. You're right. Absolutely. Plus 11. Okay. And then we have our plus c. Okay. Finally, we put our plus c in. We could have done it earlier, but then I'd have to carry it around. It would take more room. I didn't have much room. So that's our answer. At least I hope it is. So let's flip back to let's see what we got. And I don't know why they do things like this. Most of your life you've been told to rationalize your denominators, right? So how do they write the answer? 1 over 4 root 2. Write it, root 2 over 8. It's the same thing, folks, okay? It's 1, because if you multiply this by root 2 over root 2, that would be 2 over 8 root 2, 2 cancel in with this, to be 4 root 2, 1 over 4 root 2. But all your life you've been told rationalize denominators, so they wrote it otherwise. That's the same value. Inverse tangent of there it is. X minus 3 over root 2 plus. Now, here's why they did the other. We left it on the outside. If we had written this as 1 over 4 root 2, then the root 2 here would cancel that root 2. And you distribute it across, and that leaves you plus 1 over 4 times this. So, I'm going to leave the first part, square root of 2 over 8 times inverse tangent of x minus 3 over root 2. It's so slow. Plus, and then multiplying that through, that would be 1 over 4, so it's x minus 3 can't write, okay, over 4 times x squared minus 6x plus 11 plus c. Okay, so that was one advantage of leaving the root 2 in the denominator. You cancel it out over there. So let's see what we got. X minus 3 over 4 times x squared minus 6x plus 11 plus c. Got it. Make sense? So, if you wind up with a trinomial in the denominator, complete the square, and then use your trig substitution. All right, any questions on 7.3? Would you like to do preliminary? Oh, wait. Let's go and see what they have on the slide set. All right, here was their substitution. I'll blow it up. In case you're griping that you can't read my handwriting. Picky people. Okay. Our substitution was u equal root 2 of tangent theta, just like we did. Then the square root of u squared plus 2 would be the square root of 2 secant squared, secant theta. They really skipped a lot of steps to get from there to there. But it's true. And then du was that, which is true. And why did they put that in there? Anyway, I'm not really sure. But anyway. So this integral here becomes the integral just like we did. The square root of 2 secant squared theta d theta over 4 secant 4 theta. Go back and look exactly that. They pulled out the square root of 2 over 4 and put the crown over in the denominator. Why? I don't know. Okay, times the integral of cosine squared. And then they looked at the table just like Bailey did and put 1 over 2 root 2 here. Theta over 2 plus this plus c. They put the plus c in early. I should have, but I didn't want to haul it around that much. Okay? And they don't show the rest of it, but they jump right to their triangle, which is almost as pretty as mine. And if this was theta, and tangent theta is u over root 2, and that made that. And after much sweating and gnashing of teeth, we found out this is square root of u squared plus 2. That's why they did that. Okay? So, once that was done, then the integral that we started with here was 1 over 4 root 2, this thing right here. They skipped a lot of steps here. And in the book, it's continuous. On the slide set, it's hard to keep it straight because it bounces back and forth. That inverse tangent of u over root 2 plus square root 2u over u squared plus 2 plus c. Plugging in the u substitution. Okay. Then this will be this times this, which is just like it is here, and this times that. The u2's go out, the square root of 2's go out, and you're left with this plus c. And then we finally make our last substitution, and they don't show it. Okay, but we got there. All right. This is their summary. For some reason, there we go. All right. Here was the summary. If you have a square root in the integrand, a minus x squared, a squared minus x squared, you do a sign substitution. Okay? If it's a minus x squared, it's just the square root of a sine theta. Okay? You just solve one like that. So if it's a squared, then it's a sine theta. If it's a, the square root of a sine theta. Okay. You must be sweet there after you. Okay. All right. This will be the tangent substitution. This will be your secant substitution. They do your dx's there. And they also do reconstruct this to be a cosine theta, this to be a secant theta, and this to be a tangent theta. When you do this substitution. All right. That was just review. Here are the triangles we use in our review. All right. If you're using this one, if you use x equal a sine theta, this is theta, the sine of theta will be x over a, x becomes our hypotenuse. If you use this one, that's your a, x equal a tangent theta will be x over a. That makes that your radical. Oh, and if that's your x, that's your a, this becomes the square root of x squared minus a squared. If this is your x, that's your a, this is square root of x squared plus a squared. So it's the hypotenuse you add, that's your hypotenuse, so you subtract x squared from that and x squared from that. If this is your theta, this is your substitution, secant is x over a, well, secant is hypotenuse over adjacent. So x over a, that makes this side over here be the square root of x squared. Make sense? All right. Now, it's probably the most white space that we have. Let's do preliminary question. State the trigonometric substitution appropriate to the given integral. Here's the integral. Where is the integral? There it is. Okay. Couldn't see my pen. Square root of 9 minus x squared. What would be your trig substitution appropriate for that one? You tell me. No, it's not that kind of substitution. Okay, for a trig substitution, you let this variable be an angle, or have to do with an angle. A trig function. So let's let x equal what? Second, I believe sine. X equals sine, huh? Second. 3 sine. Theta, okay. Yep, that's the trig substitution used there. B is the integral of x squared times x squared minus 16. That's an ugly 16. Okay, that's really ugly. Okay, to the 3 halves power dx. Any trig substitution here? X. Okay. Whew, got the hard part done. Equal. Good. All right. Making big progress. 4. Secant theta. All right. Secant theta. If it's 16 minus x, that would be a sine. X minus 16 is secant. Okay. C. That's yes in Spanish. What would that be? The integral of x squared times x x squared plus 16 to the 3/2 power dx. Let x equal 4 tangent theta. Excellent. Okay. And then the last one, d, I'm going to write it over here, is the integral of x squared minus 5 to the minus 2 dx. What you reckon? X equal, I got that, okay. Something, all right. Huh? Something secant theta, I'll agree with that. Anyone want to help me with the something? Square root of 5, that's a good something to put there. Okay? Let's see how the back of the book did. Okay? This is 4.3, 7.3 preliminary questions. A, x equal 3 sine theta, they got that one right. B, x equal 4 secant theta, they got that one right. C, x equal 4 tangent theta, they got that one right. And D, x equal root 5 secant theta. Perfect. Good for them. All right. How about number 2? I'm going to delete this if it's okay. Y'all okay with it? Okay. Is the trigonometric substitution needed to evaluate this one? The integral of x times the square root of 9 minus x squared dx. Say again? Why not? du would be minus 2x squared. Divide out minus 2. Yeah, you got it. Yeah, not needed there. Did they get that right in the back? I bet they did. They're pretty good at it. They don't do number 2. So, no, they didn't. Okay. Number 3 is, though, express sine 2 theta. Okay, I'm getting applause. I'm happy. Okay. Wow. Okay. Yeah, that's what I said. You must be sweet. They go around honey. Oh, they also go around something else, don't they? Never mind. Okay. All right. Sine 2 theta in terms of x. In terms of, I'll write it out. X equals sine theta. So express sine of 2 theta in terms of x if x is equal to sine theta. Oh my goodness, what do they mean by that? What in the world do they mean by that? Say that again.
You gotta set sine 2 theta to x. Like,
that's exactly what they ask. How do you do that?
oh.
Define the problem well for us. Good. How do you solve the problem? I don't like what you say. Okay. Is there any way you can get that only in terms of theta? How? Sine of 2 theta is the same as two times sine theta cosine theta. Right? You don't remember it. Vaguely remember it. Huh? You just remembered it? Do you agree with it? Okay. Remember how it works? Sine of A plus B is sine A cosine B plus cosine A sine B, right? But if A is equal to B, then you have cosine A cosine B plus cosine A cosine B, or sine A cosine B plus sine A cosine B. There's two sine A, so two theta. Sine A cosine A plus two. Yeah. So you get that. All right. Now, this can be expressed as 2x, right? Because x equals sine theta. So that was taken care of. How about that cosine x? So cosine theta. Can we do that? How would you do that? Notice that little triangle there? Let's draw us a little triangle. Look, when you have these things, draw your triangles. Now, it's not that triangle. Well, the triangle's fine. The things are not. Sine theta is x. We need it as a ratio. So what ratio would that be? X over 1. Yes, let's do that. And using this theta, ignoring this and these, what would you have? Say again?
You have x.
Which one? Okay. X over here. And 1 is the hypotenuse. That's hunky-dory. Oh, so close. 1 minus x squared, hypotenuse squared minus the adjacent squared. Okay, so now what can we do? Say again? Oh, okay, let's do that. Okay, how about here? No, it's electric. Okay, no. What can you get now? What we're looking for now. Cosine theta. So what cosine theta? Oh. What? That's it, exactly. Over 1. So yeah, cosine theta is times 1 minus x squared. So there you express sine 2 theta in terms of x, when x is sine theta. That's it. Good deal. Let's see if that's what they got in the back. I bet it is, but let's see for sure. 3 is 2x times the square root of 1 minus x squared. Cha-ching. Number 4. Draw a triangle that would be used together with the substitution x equal 3 sine theta. See, 3 secant theta. Okay? So what I'm going to do is erase what we just did. All right. I've drawn the triangle for you. Actually, they did. Okay? But what would you plug where to make that true? What? Okay. How do you mean? Okay. So this becomes x over 3, right, is equal to secant theta. Hypotenuse is what? You got it. And adjacent is 3. There you go. Oh, well, let's fill out the last part of the triangle. the square root of x squared minus 9. Okay. Got it? See how that's true? They don't have that answer in the back, so you can't check it. But I feel really good about it. Okay. All right. Any questions on 7.3? Homework exercises. Do number 1. Or 3, or both. Do any of the odds 5 through 9. Do either 11 or 13, or both. Do any of the odds 15 through 31. There's a whole passel of those, maybe a passel and a half. Okay. Then try to do number 33 and or 35. Then do any of the odds 37 to 41. Either 43 or 45 or both. And any of the odds 47 through 53. I'll let you choose. All right. Also look around to see if there's potential paper topic. All right. Now, I need your feedback here. I think I know who you had for Cal 1, so I'm not really interested in yours. But Bailey, when you had Cal 1, or either one of you, as you look ahead to your engineering courses, did you have anything, or do you think you might need hyperbolic functions? Did y'all do that in Cal 1? You think you did? Okay. All right. What I'm going to do is just do a quick slideshow, but I'm not going to test you on these. And the reason is, given in the margin on page 393, the hyperbolic functions are just expressions of an exponential function. And frankly, I'd far rather work with an exponential function than have to remember hyperbolics. So do whatever you want to with them. But let me go on and get out of this. Okay. So since you did have them, we're just going to have a real quick run through of these. Did you enjoy them? Sure you did. You did? Yeah. And they were really exciting, weren't they? Yeah, okay. I thought so too. The thing is, you got to look them up anyway, because they're so close to sine and cosine. Sometimes they're the same, sometimes a little different. And just judging by how y'all deal with your sines, the SIGN signs for sines and cosines, taking derivatives and integrals, I am not about to expect you to memorize those because you have too much problem with the regular signs. So here's the deal on them. If you choose to use them or you need to use them, and you find it is necessary or required in the job, then here's what they are. The integral's hyperbolic sine is hyperbolic cosine plus c. The integral of hyperbolic cosine is hyperbolic sine plus c. The integral of hyperbolic secant squared is hyperbolic tangent squared plus c. The integral of hyperbolic cosecant squared is minus cotangent squared x plus c. Integral of hyperbolic secant times hyperbolic tangent is minus hyperbolic secant plus c, and the integral of hyperbolic cosecant hyperbolic cotangent is hyperbolic, negative hyperbolic cosecant x plus c.
I think I learned these in pre.
What's that?
Pre-cal.
You did it at pre-cal?
I think so.
Okay. You may have, but frankly, I can't even imagine coming up with an integral with any of this in it. Maybe one of those two. But the others, it just seems like an exercise in mathematics that I don't see any practical use for. Now, watch you get into your engineering courses and say, that jerk, he should have taught us this. We're needing it all the time. Well, I'm going to be back here saying, hey, sorry, folks. You paid money, I took it. If you find out you need help with it, come see me. I'll still be here for a few more years. Okay. Now.
Which, I've been telling my little brother that because he's a junior in high school, I was telling him there's a possibility for him to take calculus, like, freaking go ahead and get the credit.
Yeah.
I told him to just come there and come over here.
Yeah. Fantastic. Okay. Because y'all don't live that far away, do you?
No, I live like 2 minutes from here.
Oh, yeah. Okay.
He goes to Manuary, so he's
Yeah.
supposed to take AP calculus.
Right.
But I feel like he's just going to fail the AP exam either way. So
He's going to do what?
He's just going to fail the AP exam
Oh, he
either
is.
way, so might as well just get the credit
Yeah.
and pay for it.
Yeah. Does McAdory have that relationship with
Yeah, we have
Lawson?
a also.
Fantastic. Yeah. Send them in. Okay. Good deal. Recruit for them. Or not for me. Okay. If you're doing hyperbolic substitutions, then this would be hyperbolic sine. Why would you want to? You can use a hyperbolic tangent and they're easy. Why would you want to introduce a hyperbolic sine and then have to remember all more stuff? It works really well with hyperbolic tangent. If you had this form, you could use that. Why would you? Because this works really well for a regular old secant, right? So why, this section to me is superfluous. Why would you introduce some other way to do it when we already got a way to do it? And y'all are really good at it, putting the things in, okay? So why have new things? Okay, never mind. I don't know. It's up to you. All right. These are just some examples that I'll blow it up. So if this is your problem to do, why do you have to provide cosine? What would you use? Tangent. What would be the substitution? For tangent. Yeah. Why do that? I don't know. It makes no sense to me. Okay? If you ever need them, here they are. And frankly, if I ever needed them, I'm going to look them up anyway, because I don't want to trust my memory till I got the sign right for this. Yeah. I'm going to look it up. Okay? So if you ever do need them, look them up. Okay? This one, I would use what? Tangent. This one? Secant. This one? I think I'd use sine. See what happens. It might work, it might not. I'd use sine for that too. This one? I would try sine. It may not work for you. Maybe this is easier. I don't know. Okay? This one? I would try tangent. It may not work, but I'd sure try that before I try this. Okay? But if you want to use them, you sure can. They're there in any table you want to have. But, all right. Now this might be worth just even looking at this section. This is good old, he's one of the most handsome characters I think I've ever seen. Leonard Euler. Okay. Mr. Universe. Okay. All right. It looks like he's Euler, but it's pronounced Euler. He used to play for Houston. Okay. He ranks among the greatest mathematicians of all time, right up there with Newton and Archimedes. He is out there. His work, printed in more than 70 volumes, okay? He published like crazy, okay? Contains fundamental contribution to almost every aspect of mathematics and physics of his time. The French mathematician Pierre-Simon de Laplace once declared, read Euler, he is our master in everything, and he really was. It was just incredible. If I remember correctly, I'm not sure, but I believe he went blind in one eye, and he still produced. And then he went blind in the other eye, and he still produced. He had a photographic memory. He didn't have to see it. He just told the scribe what to write, and it was usually correct. If he's the one I'm thinking of, when he was a boy, his father was a bookkeeper, an accountant type person, something like that. And as a little boy, he was playing around when his dad was at work, and he looked over his list of numbers and said, "Dad, you made a mistake there." His dad looked, he didn't even know he could add that kind of stuff. He went back and checked, and sure enough, he pointed right where the mistake. And I think, maybe getting him across that with someone else, he was the one when he was in elementary school. The teacher was having a bad day, didn't want to teach. So he said, okay, write down every number from 1 to 100. Add them up. He thought this will keep the bookers busy for at least an hour or so. In a few minutes, Euler gave him the correct answer. Now, how he did it? No, that was Pascal. Okay. Okay, if you're adding 1 to 100, okay, let me get my pen activated. I shouldn't be wasting time with this, but it's fun. Okay. We're going to do 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 11 plus 12 plus 13. We'll keep on going, and you have to do so. Ultimately, you're going to have 100 plus 99 plus 98 plus 97 plus 96 plus 95 plus 94 plus 93 plus 92 plus 91 plus 90 plus 89 plus 88. Okay. Right? And you had those other numbers. I just ran out of room. But look at here. What's 100 plus 1? 1 plus 100. Plus 2 plus 99. Plus 3 plus 98. Every one of these pairs to that, doesn't it? So how many you got? Until you get down to 50 plus 51, right? So you have 50 numbers times 150 times 101. Well, I could probably do it faster than me. $5,050. Okay. Pretty sharp little cookie, wasn't he? I never would have thought of doing that, especially in elementary school. Okay. So, sorry to take time for this. If you haven't chosen a favorite topic, Euler is an incredible character. Okay? If you have one, that's fine. Or, Simon de Laplace, he's a great character. Things that Euler is responsible for. What's the natural base of our number system? remembering one's rule. Okay. What's the natural base of our number system? Okay. Okay. We use the base 10 number system. Okay. That's because we have 10 figures. But things don't really work out well in that. What's the natural base of our number system, especially in calculus sense? E. Remember, integrate E, differentiate E. E, just everything works around E so nicely. Why do we call it E? He discovered it. Quite a character. Okay? Amazing. His last name, yeah. Wow. Okay. Or that's my understanding. Anyway, let's move on. This is differential equations, I think. So, not even going to mess with that yet. You'll take a course in that. Okay. Now, here is something that's worth zooming in on. You're probably familiar with this, right? I, imaginary number. Now, let me think. If I'm not mistaken, it may be that Euler was the one who really started using that. I'm not certain, but he may have been. Okay? Now, this is something you'll run into. I don't want to spend a lot of time on it because it's not in this course. It is in the book right here. Euler's number with the imaginary number, which I'm almost certain he had a lot to do with it. He didn't come up with it, he had a lot to do with it. Here's one way to express it. This is in the imaginary form. This is in real numbers over here. We came up with this. Okay? And it didn't take much from there. A little bit. Here now you have real and imaginary parts with that same sort of expression. He probably came up with that one as well. But here is a one that is, I don't know if you've talked with many mathematicians. I can't get this thing to work. Is it time? What do you say? Oh. You what?
He was in my trade class.
Who?
I got to study to be a mathematician.
Oh, okay. Yeah. Here is, this is often called, I think it's Euler's formula or Euler's equation. Euler's formula. Okay? Well, actually, the previous one, but this one too. If you think about this, the three perhaps most celebrated numbers, this is an irrational number, E, 2.7, blah, 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 blah. Pi, 3.1416, blah, blah, blah. I square root minus 1, you can't express that, okay? And just a regular number, -1. That formula is incredibly, it's what mathematicians call an elegant equation. It's simple, powerful, in some senses beautiful. Total elegant. Euler's formula. Now, so some of the topics, you could write on Euler, on Laplace, on Euler's formula, on development of E, Euler's use of I. There's about a dozen paper topics we just talked about. You could choose any of them, or none of them. You may have already chosen your paper topics, but it's pretty incredible. That was worth it just for that, okay? How they move from hyperbolic to there, I don't know, but anyway. I'll put it this way, I'm not going to test you on hyperbolics. You can certainly use them if you want to. Since Mr. Racy loved them, right? I take it. Huh? Okay. She what? Yeah. Okay. And there's nothing wrong with going by the book, but every one of those examples we saw, just about, you could work with trig substitution. So why introduce another substitution? And you are in here one. Hyperbolic, sines, cosine, tangent, secant, and sec, they're very similar in the properties of sines and cosines, the tangent, the trigonometric ones, except a few signs are different. And I said, y'all have such trouble with the signs anyway, with your sines and cosines, I didn't want to introduce another one in there. So, I'm sorry, I'm making it seem like. All right. What did I just do? I must have gone back to the same one I was in. Oh, I know what happened. It didn't close out all the way. There it goes. Let's move to 7.5. All right. This one. I wondered why it was already from current slide. All right, here's another method, another technique for doing integrals that are really tough to integrate. Okay? And these are a little bit background. Let me just get out of this. Okay. Remember, sometime in your past, you probably had, say in pre-calculus algebra or somewhere, you studied functions of this nature. What do we call those? Okay. This could be called a fractional form. So there's another name for it that could be a blank of p to q. Ratio, right? Ratio is a division type thing, right? So what kind of function would you call that? Okay. Let me first take P and Q are polynomial functions. Most of the time we have capital letters for a function that means polynomial. Maybe not always, but a lot of times. Especially if it comes to P or Q, almost always say polynomial function. And since they can't use P again, they do the next letter, PQ. So Q, capital Q would be a polynomial. So the ratio of two polynomials, functions, rational function. Exactly. This is what we call a rational function. So the method of partial fractions is the technique we use when we have a ratio of rational function. When we have tried to integrate rational functions. Okay? Now, here's an example. Here's a very simple rational function, 1 over x squared minus 1. Okay? Now, I don't know, you might be able to work that using a trig substitution as in secant, possibly. But here's another technique. Now, would you agree that this is the same as 1 over x plus 1 times x minus 1? Yeah. You just factored that denominator. Would you also agree that there could be, somewhere out there, a fraction say A over x plus 1 plus B over x minus 1 that would give you that form. Because if you were trying to add these two fractions together, you could at least have a denominator, which is the product, and then you would do A times this one plus B times this one, and figure out what would equal 1, right? Okay? Well, that is a technique we're going to use, okay? We're going to rewrite fractional forms, factor the denominators, if it's possible, okay? Factor as much as possible. And once you get it in factored form, then split it into fractional pieces that have simpler denominators. And guess what? If you're trying to integrate this, isn't it easier to integrate this? It's going to be a log, A times the log of this, right? Plus B times the log of that. It's real simple to integrate. Whereas this, even if you could get a trig substitution, it's sort of long and kind of messy. Okay? So why not do it simply? We get a little lazy. Okay. So let's see if we can solve that problem we just did. What would the A and B be? Didn't we just say it would have to be A times x minus 1 plus B times x plus 1 over x plus 1 times x minus 1. Do you agree that that would be how we did it? Okay. Because if you just do this part, that would be A over x plus 1, right? Plus B over x minus 1, right? That would be exactly that. Yeah.
Wouldn't it cross out?
What's that?
Wouldn't the denominator cross out with the...
Yeah.
Wouldn't like x minus 1 cross out with x minus 1 in the denominator?
You mean divide out this and that? Or are you saying once you separate it? See, if you wrote this as two fractions, A over x minus A times x minus 1 over x plus 1 times x minus 1 plus B over x, B times x plus 1 over x minus 1 times x plus 1. If you split them out that way, yeah, then you divide out. But like you've written here, you can't, because you can only divide out things that are multiplied. There are no common factors up here. So you can't just say do that. See, I don't like to cross out, because that's not a legal mathematical term, crossing out. You can divide out, but you can't cross out. Okay. So, do you agree that this is the same as that? Yeah. Okay? And we want it to be that. So if it's going to be that, let's go and multiply this out. This would be AX minus A plus, you finish, BX plus B over that. I'm not going to write it all out. And if we want that to be 1, what does that tell you? That AX plus BX has to be 0, because there's no 0 term up there, right? So that means A plus B is equal to 0. Would you buy that? But it also means that minus A plus B must be equal to 1, because those are your constant terms. And the constant is 1. Okay? Well, if this says that B is equal to A, right? If you add A to both sides. And this then says if A is equal to B, then this is a plus a, because a is equal to b, is equal to 0. Well, either a is equal to 0 or, wait a minute. I've done something backwards here and I can't see where I did it. Minus a plus b. Oh, wait. Here. Did it backwards, yeah. Not that way. A plus a is equal to minus b. That's it. So a plus b is equal to 0. A is equal to minus b. So then up here, we put minus b, minus minus b, which is plus b. Right? Plus b is equal to 1, 2b is equal to 1, b is equal to 1 half. A is equal to minus 1 half. So that gives you minus 1 half over x plus 1 plus 1 half over x minus 1. Okay? And that's exactly what the yeah, I just wrote it backwards from what they did. Okay? Yeah. Now, trying to find where they got this. Okay, I don't see it. So let me erase some of this stuff. How are we doing on time? Yeah. I don't think we need that anymore. And, oh, maybe we do need that. Yeah. Okay, we've already used this, and that, and that, and that. Sorry about this small screen. That's the only disadvantage. This computer has even a smaller screen than my computer did. Okay. Yuck. Okay. Okay. So we did this work. So my original thing, what if this was the integral of that? Now we've changed it to be the integral of this. Okay? And we can do that integral. Okay? What is the antiderivative of minus 1 half? Let's break this down a little. Be minus 1 half times the integral of dx over x plus 1 plus 1 half times the integral of dx over x minus 1. Can you do these two? What this will be? Huh? Take the derivative of 1, you get this, right? Derivative of 1 is 0. The antiderivative of this.
X squared plus x.
Okay, take the derivative of x squared plus x, you get 2x plus 1. Not 1 over x plus 1. Antiderivative of 1 over u du. Second? Log. So this would be minus 1/2. What are you doing? Okay. Minus 1/2 the log of, and usually put logs in absolute values, x plus 1, plus 1/2 the log of x minus 1. Right? Now, if you wanted to use the rule of logarithms again, that would be the log of x plus 1 to the negative 1/2 power plus the log of x minus 1 to the 1/2 power. You could write it that way, but however you write it, just put a plus c at the end. Or you could put plus log c and then you can fiddle around and do other things. But that's how you go about integrating. They didn't put their logs in there and they left it with the 1/2 coefficients. But that's what they get. Now, here is a fact from algebra known as the fundamental theorem of algebra. Every polynomial q, remember the q was 1 in the denominator? Every polynomial q with real coefficients, that means it can be positive, negative, fraction, decimal, rational, or irrational. You just can't have any i's in it, okay? Real coefficients can be written as a product of linear and quadratic factors, okay? They may be messy, but you can write them as a product of linear and quadratic factors with real coefficients, okay? However, it is not always possible to find those factors explicitly. They can be done theoretically. We're going to deal with ones you can't find, okay? Now, let's talk about a couple of other things. Let's see, I don't think it's written here. No. So let's, all right. Does anyone, okay, remember our rational functions. F of x equal p of x over q of x. Now what are the p's and q's? Second? Which guy? That's the rational. F is rational. What are P and Q?
Ratios.
Second?
Ratios?
It's a ratio of those two, but what are P and Q? P is the first letter of what kind of function? Polynomial function. So P and Q are polynomial functions, right? Now, what we just were reading is that every polynomial function with real coefficients can be written as a product of linear and quadratic factors with real coefficients. However, sometimes they're hard to find. Okay. Now, here's something else. Would this be a rational function? X squared minus 3x plus 7 over x fourth minus 16. Is that a rational function? Yeah, polynomial over polynomial. What might you do to that to simplify a little bit? Factor what? Yeah, I can't factor the numerator. Maybe you can. The bottom, okay? How does it factor? Very good. Are you through factoring? No. How? Leave the x squared plus 4. You can't factor that anymore. That's the sum of two perfect squares. No factorization there, but x plus 2, x minus 2. Guess what we just did? We factored a fourth degree polynomial into a product of linear and quadratic forms. That's what fundamental theorem of algebra says you can always do. Sometimes it's hard to do. This one was fairly easy, right? Okay. How about this one? 2x squared plus 7 over x minus 5. Is that a rational function? Yea or nay? It's a polynomial. Whether you can factor it or not, that's a polynomial, that's a polynomial. So this is a rational function. But you're right, you can't factor either the numerator or the denominator. Denominator is in prime form. Numerator is no factorization for it. No easy factorization for it. But who cares? All we're interested in is the denominator. Remember, it's the Q of x, the denominator. But what's wrong with this? Nothing really wrong with it. But this is what we call an improper rational function. This was a proper rational function. Okay, now wait a minute. With fractions, I remember, give me an improper fraction. 7 over 5. Yeah, a proper fraction. 5 over 7. Okay. There, the denominator needed to be greater than the numerator for it to be proper. If the numerator was equal to or greater than the denominator, it was improper. Well, we don't have that in polynomials, but we do have degrees. What's the degree of this numerator? 2, degree of the denominator. 4, as long as the degree of the numerator is less than the degree of the denominator, that's a proper rational function. How about this one? Why? This is improper. So what could you do to that to make it proper? One of our favorite operations of all time. Dividing polynomials. Remember how much fun they were? Yeah. Okay. Now this one, actually, you can use synthetic division, can't you? Remember that? Yeah. Which you want to use, long division or synthetic? Synthetic. How do you do synthetic? Okay, no, you're doing long. You want to do long? Okay, let's do long division first. Put x minus 5 on the outside. On the inside, you put 2x squared plus 0x plus 7. You have to account for every term. And when you're missing the linear term, you have to put it in with 0 coefficient. Coming back? Yep. There you go. Okay. So let's proceed to divide. X will go into 2x squared how many times? 2 x times, right? Then you, okay, let's go back to long division. Let's do 15 into 27. How do you do that? They'll go one time. Then you multiply 15, then you subtract, and you get a remainder of 12, which you could write as 12 over 15, which you could simplify to be 3 4 over 5, yeah, 4/5. 1 plus 4/5. Okay? Oh, okay, what do you do then? Multiply. 2x times x is 2x squared. That's exactly what we want it to be. And 2x times negative 5 is negative 10x. And then you subtract. But now you got signed numbers, okay? So with signed numbers, I prefer to change signs and add. That's how you do subtract signed numbers, right? Okay? So these go away. Fantastic. We wanted them to. What does this give us? 10x. Bring down the 7, and then you do it again. X will go into 10x plus 10 times, and then you multiply. 10 times x is 10x. 10 times minus 5 is minus 50, and then you change signs and add. Okay? That goes away, and this will give you plus 57 as a remainder, right? Or you could write that as plus 57 over x minus 5. So guess what? You've rewritten this as, this was an improper rational expression, rational function, and you wrote it as a linear function plus a proper rational function. Now, if you're integrating this, you can integrate that. That would be x squared. Integrate that. It would be 10x. And then you can integrate that. That would be plus 57 times the log of x minus 5. Look at that. Pretty easy, huh? So that's what you do if you have your rational function is improper. Divide first, and then integrate whatever else what you have after the division. Okay. How about this one? You've done it again, haven't you? You let me run over. Y'all just have too much fun. You got to quit doing that, okay? All right. We'll pick up next time with that last rational expression. Okay. Is this dragging too much? Do we need to speed up, or is the pace okay? Huh? Okay. You're easy. Okay. All right. Good deal. We will see you on, what is the date? Next week. Okay. So try to get working on your test, because believe it or not, we've got this section, 7.6, and we're not going to do a lot with improper integrals. I'll go over them quickly like we did the last section, and I think that's going to be it. No, probability and integration. I may just do a slideshow on that, but you're not going to be responsible for that on the test either. Numerical integration, yeah, we're going to jump to that. We'll do that. So we'll go through we'll do this section and the next one, go through the next two real quickly, maybe not at all, and then the numerical integration. Okay? Good deal. All right. Have a good weekend. Of course, working on calculus will make it a good weekend, won't it? Yes. Okay, good deal. Carry on.